We choose to examine a phenomenon that is impossible to explain in any classical way and which has in it the heart of quantum mechanics, said by Richard Feynman. Physics has this reputation. It's like the A-plus student of the science world, the know-it-all, dependable kind of science. For centuries, classical physics was the law of the land, governing everything from apples falling to the ground to planets cruising around the sun. But like any good overachiever, it eventually cracked under pressure. By the end of the 19th century, classical physics faced an existential crisis. The perfect machine of classical physics couldn't explain some weird behavior in the world of tiny things, especially when it came to light and heat. In the late 1800s, physicists were investigating the phenomenon called blackbody radiation. A blackbody is an idealized object that absorbs and emits all types of electromagnetic radiation, like heat or light. Think of a blackbody as the universe's ultimate heat sponge. If you heat this blackbody, it should start radiating energy, much like an oven. Classical physics could describe how much energy was radiated at different temperatures, but when they tried to calculate how much energy came from different colors of light, they ran into a major problem. You see, the color of light corresponds to its wavelength. Red light has long wavelengths, blue light has shorter wavelengths, and ultraviolet light has even shorter wavelengths. The classical approach, known as the Rayleigh-Jeans law, predicted that as you increase the frequency of light, moving from red to blue to ultraviolet, the amount of energy emitted should just keep getting higher and higher, which makes sense, right? Higher frequency means more energy. But when you push that idea to its extreme, looking at super short ultraviolet wavelengths, you get an absurd prediction: the energy emitted should become infinite. This was the ultraviolet catastrophe. Scientists were baffled, their calculations leading to an impossible conclusion that defied the very principles of physics they had relied on for centuries. Then came Max Planck with a groundbreaking idea that would change everything. He proposed that energy is quantized, meaning it comes in discrete packets called quanta. Why was this a catastrophe? Infinite energy means everything should explode, which, if you're sitting in your living room right now, clearly hasn't happened. Every time we switch on a light or heat up the stove, we're dealing with radiation, and somehow the world keeps spinning. So what actually was going on? Classical physics was completely failing to explain what actually happens when an object radiates light. It predicted an explosion of energy in the ultraviolet range that doesn't happen in the real world. Something big was missing from the equations. To put it in perspective, imagine if every time you turned on a light, it unleashed an infinite amount of energy. Not only would your light bulb be obliterated, but your entire house would be incinerated in an instant. Clearly, that's not our everyday experience. The predictions of classical physics were not just a little off. They were wildly incorrect, pointing to a fundamental flaw in our understanding of energy and radiation. This wasn't just a minor hiccup. It was a full-blown crisis, threatening to unravel the entire fabric of classical physics. Scientists were left scratching their heads, desperately searching for an answer. At this point, physics was in full meltdown mode. But in 1900, a German physicist named Max Planck decided to take the wheel and drive physics right off a cliff. And in the process, he invented quantum mechanics. How did Planck save physics? He introduced this insanely bold idea. Energy isn't continuous. Instead of being a smooth, never-ending stream, energy comes in tiny little packets or chunks called quanta. In other words, energy is quantized. Planck suggested that if you heat an object and it starts radiating energy, that energy doesn't just come out in one big wave. Instead, it's spit out in discrete packets. Think of energy as a bunch of individual coins instead of an infinite string of pennies. You can only have whole coins, no matter how small. But Planck didn't stop there. He also gave these little packets of energy a name. He called them photons, though the name came later. And he said that each photon carries an energy that depends on the frequency of the light. Planck's quantization was the magic bullet that solved the ultraviolet catastrophe. This meant that high-frequency light, like ultraviolet light, required significantly more energy to be emitted. Think of it this way. If you want to emit ultraviolet light, you need to pay a hefty energy price. The higher the frequency, the more expensive the energy chunk. This effectively limits the amount of radiation that can be emitted in the ultraviolet range, preventing the infinite energy nightmare that had troubled physicists. In simpler terms, light doesn't go haywire in the ultraviolet spectrum because the energy chunks needed are too large for the object to handle. Planck's new physics ensured that the energy emitted by blackbodies at high frequencies was not infinite, but quite finite and reasonable. Planck had no idea what he was unleashing. He was just trying to solve a stubborn problem, but in the process, he introduced the world to quantum physics, a weird, counterintuitive, and mind-blowingly accurate theory that explains the behavior of the tiniest things in the universe. But what's crazy is that Planck's solution didn't sit well with him. He wasn't a fan of the whole quantized energy idea, even though he invented it. He thought it was a temporary fix, something future physicists would find a concrete solution for once they figured out the real explanation. Because soon enough, this tiny crack in the wall of classical physics became a gaping hole, and quantum mechanics started taking over the world. Einstein would use quantum ideas to explain the photoelectric effect, how light knocks electrons out of metal, and Niels Bohr would use them to develop a quantum model of the atom. To truly appreciate the revolutionary nature of Planck's discovery, let's take a moment to compare classical physics with quantum physics. Classical physics, also known as Newtonian physics, is built on the idea that the universe operates like a well-oiled machine. Objects have definite positions and velocities, and their future behavior can be predicted with great accuracy using the laws of motion and gravitation. This deterministic view of the universe was comforting in its predictability. Quantum physics, on the other hand, tells a very different story. At the microscopic level, particles behave in ways that defy classical intuition. Electrons, for example, don't have definite positions or velocities until they're measured. Instead, they exist in a fuzzy cloud of probabilities. This is encapsulated in Heisenberg's uncertainty principle, which states that you can't simultaneously know the exact position and momentum of a particle. Furthermore, in the quantum realm, particles can exist in multiple states at once, thanks to a phenomenon called superposition. They can also become entangled, meaning the state of one particle is instantaneously connected to the state of another, no matter how far apart they are. This is what Einstein famously referred to as spooky action at a distance. The divergence between classical and quantum physics isn't just about different rules. It's about fundamentally different worldviews. Classical physics sees the universe as a clockwork, while quantum physics sees it as a complex, interconnected web of probabilities and uncertainties. So, why should you care about the ultraviolet catastrophe and Planck's solution? Because this was the moment physics had to face the fact that it didn't know everything. The neat, orderly world of classical physics, where everything is predictable and works according to simple rules, broke down. And in its place, we got quantum physics, a theory so strange and counterintuitive that even today, we're still trying to fully grasp its implications. Classical physics may have melted down, but in its ashes, quantum mechanics rose, and with it, a new understanding of the universe, one where energy comes in little chunks, and the world of the very small is anything but simple. This shift didn't just change physics, it changed everything.